Still loading for me. Oh, there we go.
Okay.
Yeah, that's good.
Okay.
Yeah, okay, great, great. Okay, so let's start. And today we are gonna start with energy momentum tensor. And like the basic idea behind it is actually like some kind of the energy density. You remember like from the electromagnetic theory, then there we have like continuity equation about like the change of the charge density like in a small box. It equals to the divergence of the current fluxes through that box. So you can imagine it like a box, and inside box you have some charges, and like the change of charges inside the box equals to the three currents going through like 3 dimensions out of the box, and that's kind of is described by continuity equation, something like d rho by dt equals minus divergence of j, like of sum of the currents basically. And like from the perspective of the differential forms, we can interpret like those two quantities like rho and j here as one for vector j, and in terms of differential forms we can think about that as one form or three form, dual to this one, like Hodge dual one. And we have seen that in like pictorial representation we can think about those as like some closed form in the space-time. So if you will think that we have space-time here, then that equation will just be described like d star j equals 0. So like that star j is the closed form here. And we'll have something like some lines, closed lines going to infinity or maybe looping somewhere, I don't know. So like that's the basic picture. And to understand energy momentum tensor, we need to go from here to the more general situation. So basically, in this case, instead of having like one continuity equation, we have like 4, basically. And you can see that this equation is really similar to the continuity equation for current, basically. But we have one additional index b here. And we are obtaining that index because of the quantity which is conserved in that case is no more a scalar quantity. And this quantity is like 4-vector quantity described here called PA, and that is the energy momentum for vector basically, or for form basically. Well, it's bad to say like that, so like for covector in that case. Sorry for such puns here. Anyway, we have something which is called like 4-vector, and which describes like energy momentum. And in that case, we can kind of think about that thing being conserved in a space-time box. So basically we have some kind of like 4-dimensional space-time box, and we have something which is called like energy momentum vector inside, and that 4-vector, it will have different basically fluxes through the different dimensions, and we will have 4 dimensions like time, x, y, and z here. And therefore basically that tensor TAB will describe for us how much that quantity, that 4-vector and like different constituents of it will change depending on the like dimension. So for example, like in the space-time we will have like 16 4 by 4, right? Yeah, 16 values there. Basically, it will be like t, tt, t, xx, t, yy, t, zz, and here we'll have like t, xt, ty, oh, sorry, tyt, and t, zt, and like symmetrical quantities here like t, tx, t, ty, t, tz, and here we'll have like spatial how to say that, like spatial terms like txy, t yx. Let me think about it one moment. Yeah, I just wrote matrix a bit clumsy here, so like we need to have like txx here, tyy here, and tzz here. Yeah, and therefore we'll have something like tyx here and tzx here, tzy probably here, yeah, and txy and tx that here, no, or
yeah, that looks
yeah,
right. And
yeah,
then
yeah,
ty.
yeah, and tyz here. So basically, you will have something like that, and I really advise you to take a look at the Scienceclic, something like that. I don't remember like the right name for the channel. I've sent the link for you in the chapter 19 for the playlist, and that channel has like really great introduction, and probably in the video number 6 it contains the explanation for the energy momentum tensor in those quantities. So basically we can think about the energy and like so probably I need to start from the electromagnetic field analogy. Like in electromagnetism, we have basic like thing which kind of introduces the electromagnetic field, and it is charge. And basically, like flow of the charge in a space-time is conserved, and like the presence of electric charges, it produces electromagnetic fields. And in the case of the gravitational field, we have this similar situation, but instead of the charge, like we have the mass, and mass is energy. And basically, therefore, we can kind of demonstrate the distribution of energy as the, distribution of mass as like the movement of the energy in a space-time. So basically, that tensor to form in that case will describe for us how like energy and momentum changes depending on the direction. So basically, like that first thing called energy density here, like TTT, it just describes how time component of the energy momentum for vector changes through the time direction. And those three quantities and similar but like symmetrical one to those like txt and ttx here, they are momentums basically, like momentum densities, something like that, and basically they describe how like x component of the energy flow is changed with time. So like all of those numbers, they're kind of describing the movement of the flow of the energy. So basically you can think about that like a fluid in the fourth space-time, something like that. And therefore we will have like similar things here in terms of fluxes. So basically we have some kind of the density here. Those will describe fluxes. And that 3x3 matrix will correspond to some kind of like transfer of the space components of the energy through space. And if they're the same, like on the diagonal here, like txx, tyy, and tz, then we will have what is called pressure. So basically, on the diagonal here, we have pressure, and those upper and down triangular terms are called like viscosity. And basically, I think that like the metaphor of the fluid is really applicable here, and therefore, like those terms are analogic to the movement of some kind of a fluid in a space. Yeah, so that was like a short introduction, and basically that's like probably the first half of the 19.5 here. So here you can see the continuity equation for that like energy momentum tensor here. Yeah, and like the basic idea that we need to consider the equation of the energy density of a field, and this density being the source of gravity. So that's like the basic idea here, that mass is the energy, and we can encode the mass distribution with energy distribution. And that's done by energy momentum tensor. We have that continuity or conservation equation here. Later, it's described in terms of the like current analogy, like GFA and continuity equation from electromagnetism. And also it's explained here why we have additional B index here, because of the 4-vector conservation instead of the scalar things. And if you'll go further, yeah, here is described the same thing about pressure, and I also wrote here about viscosity terms also, just as the remark. Yeah, so basically that's it. And for Maxwell field, we can calculate the energy momentum tensor using the Maxwell tensors, and it's done through that formula. So basically here we need to believe in it, and if we do not believe in it, to consult some additional sources to prove that. But the basic idea here is that if you have like different physical fields in the space-time, we can calculate their energy momentum tensors and just add everything together and obtain like the full energy momentum tensor for all of the fields in the space-time. And that tensor, the full one, should satisfy the conservation equation. Yeah, so let's stop for a moment here. Maybe you have some questions. And I will recheck for a moment. Maybe we have new members on the call. Oh, we have Chris also today. Hi, Chris. We cannot hear you for some reason, but anyway, we are happy to see you.
Yeah, sorry I haven't joined in a while. I also admittedly have not read the current chapter that we're on, but hopefully I can get back into the schedule.
Yeah, that's okay. Actually, like a lot of people on today's call haven't read that yet, so I'm basically explaining that in simple terms as far as I can.
You're in good company, Chris. Thanks.
Probably I will make Chris a little bit louder on my computer because... Yeah, okay, so I hope you understood the analogy here. Yeah, and basically the second half of the 19.5 here is about the problem with the energy momentum tensor of the gravity itself. And the problem here is that in the presence of gravity, we will have like a curved Minkowski space with a curvature, and that conservation equation here will not guarantee us that we will have like the integral conservation law, as we have seen in the previous subchapter there. something like that. So basically, it's like a sum of the currents and like charges is conserved or not changed in the time. And the reason for that are those like Christoffel symbols from the covariant derivative there, and that thing kind of ruins. It prevents like the two form TAB. Like that extra index there prevents it from being the dual of the three form, and we are kind of cannot use the Stokes theorem there. So basically, it seems that we are losing like the most crucial conservation laws of physics, like the laws of conservation of energy and momentum. And as a partial remedy there, we can use the Killing vectors. And just to remind you, like the Killing vector is the vector for which lead derivative of the matrix equals 0. So basically, like you can see that equation at the bottom here, and it kind of means that if we'll transport metric, as far as I understand it, yeah. So basically, if you will transport like metric over one direction of the Killing field and over like another direction of the Killing field, then like basically matrix will not change. So you kind of can use Killing field and transport metric over that, and metric will be preserved as far as I understand that. And basically by using those Killing vector fields, we can kind of deduce like some kind of the basic symmetries of the Kerr-Minkowski space, and therefore we can use some kind of the Noether theorem to deduce the conserved quantities, and from those we can obtain integral law, which we kind of were losing in the previous paragraph. And Penrose just like give us the answer here in the explicit terms. He calls those quantities LA, and those are like good enough to be like one forms, and therefore we can form like a dual three form for those and obtain similar integral law which we wanted to, and basically have something like continuity equation here. Yeah, but there is a but for those that like as far as I understand that he just describes here that space-time is just a background for the fields or something like that. So I'm not kind of understand that like why it prevents us for using those Killing vector, but basically he says that nevertheless like they will not help us in understanding the fate of the conservation laws when the gravity will become like an active player on a stage. So basically he says that if gravity is present, then we will still have like missing symmetries there. And historically it was like in the early days of general relativity, it evoked some of the strongest objections to that theory and reasons for unease with it, as expressed by numerous physicists over the years. And basically, he just promises here that he will explain everything later at the end of the chapter in 19.8. We will see how to take care of energy momentum tensor for the gravity and how gravitational energy comes into play. So basically we kind of need to wait for those. Yeah, so, and here he just says that only non-gravitational fields currently for the current moment of time will be included in the energy momentum tensor. And he also says that in a case Yeah, he also says that we can. One moment. Yeah, so basically he says here that whatever energy there is in the gravitational field itself is to be excluded from having any representation within it. And this point of view is made somewhat plausible if you think again of the principle of equivalence. So basically, if we imagine an observer in a free orbit, say within some spaceship without windows, so it appears, at least to a first approximation, that there is no gravity field in a ship. That observer would expect that energy is conserved within the spaceship and would therefore expect that equation, this one, holds, and without there being any contribution from the gravitational field. So he kind of explains that like non-including of gravitational field into energy momentum tensor here from that viewpoint, from the principle of equivalence. And he says that anyway, this conservation is, however, only an approximation, and the tidal forces, which we have seen in the chapter 17, they will come into play anyway, like when that orbiting ship will have some like planet gravity applied to itself. And to care of those, he once again just basically says that we'll need to wait for the 19.8 there, and that those gravitational contributions to the energy will kind of slip in through the cracks that separate the local equation from an integral conservation law of total energy momentum. Yeah, strange phrase. You kind of can ignore it, I think, and we will discuss that question at the end of the chapter. Yeah, so that's it with 19.5 and this stress energy tensor. So basically, like the main idea here, just to conclude, is that like mass is kind of the charge in the gravitational field theory, and energy momentum tensor describes the density of the mass, basically, and therefore energy in the space-time, and kind of the flow of those. Yeah, and we will need it later to derive Einstein field equation. Any questions? Okay, then give me a brief moment. I will pour some water and I'll be back like half a minute. Okay, I'm back. So the next chapter is about like deriving. It's kind of sounds really strong, like deriving the Einstein's field equation, but basically it's kind of really loose derivation. But anyway, like so. The first part of the 19.6 is about tensors, basically. Like, why do we use tensors here? And like the basic reason here for using the tensors, which Penrose is talking about, is that we need to describe four-dimensional curvature, and like tensors are the natural instrument for doing that. And that curvature will give us like the description of the tidal forces we have seen in chapter 17. Yeah, and another perspective on that is that like from the principle of the equivalence, like gravitation is not to be regarded as a force for the observer who is falling freely. uh, yeah, there is no gravitational force to be felt, and instead gravitation manifests itself in the form of space-time curvature. And he says that it's important, if this idea is to work, that there be no preferred coordinates in the theory. So basically we don't have like any preferred coordinates for our space-time because of that principle of relativity and principle of equivalence. And from those principles we need some kind of the invariant quantities there, and tensors are those kind of the invariant quantities. And that principle, which is called like the principle of general covariance, it tells us that not only there are to be no preferred coordinates, but also that if you have two different spacetimes representing two physically distinct gravitational fields, then there is to be no naturally preferred pointwise identification between the two. So we cannot say which particular spacetime point of one is to be regarded as the same point of some particular spacetime point of the other. It kind of sounds to me really similar to the sentence he been talking about the Galileo's relativity, actually. Yeah, I'm still not sure about that identification, but as far as I understand that, I'm kind of more influenced here by the Chris's videos about invariance and like covariance and contravariance. That basically we need invariant quantities here because of the like non-independence of the coordinates. And basically like that's the second reason to use tensors. Yeah, and in the next paragraph, some requirements are described. And the first one is that source of gravity should be the energy momentum tensor. So basically, like the mass or energy will create like gravitational disturbances for us, and it needs to be subject to the continuity equation, or that conservation here, and that in the appropriate Newtonian limit, like for the small velocities, we must return to the we need to obtain like standard Newtonian gravitational theory. Okay, so those are like two basic requirements to start from. And in the previous chapters, we have seen that in Newtonian theory, there is a volume reducing effect for geodesics that are neighboring to, and which are initially parallel to an observer's geodesic word line. And those neighboring geodesic accelerate relative to gamma in such a way, gamma here is word line of the observer, in such a way that the space-like 3 volume that they enclose has an overall acceleration that is equal to minus 4 pi g delta m here, where delta m is the active gravitational mass within the volume enclosed by the geodesics. So basically we have like change in the volume described by that equation here in the Newtonian theory. Yeah, and now we need to use the curvature somehow here, and to use it, Penrose kind of converts it to the Ricci tensor, and he says like the key geometrical fact is that this inward acceleration of volume that occurs in this situation is measured by the 0-2 valent, basically two-form tensor called the Ricci tensor, which is defined as the contraction of the original Riemann tensor. And in that case, like we can prove that the same, here it is, like the acceleration of volume starting from the rest is given by that formula. And d capital here represents the rate of change with respect to the observer's proper time. So basically it's like a derivative here, second derivative. Yeah, and in that case we will have like Ricci tensor here, and also, as far as I understand, those are like 4 vectors, some kind of the probably like basic how to say that, like 2 vectors for 2 closed geodesics, which are kind of border the volume, as far as I understand. Yeah, and basically, let's see further. Yeah, so he talk about the mass here, and he says that the mass density as measured by the observer is the 0,0 component of TAB in the observer's local frame, and this is just the quantity TAB TATB. So the mass within the volume enclosed by the neighboring geodesics is okay. So he kind of, by using energy momentum tensor, we kind of can deduce the change in the mass using the change of the volume. So basically you can consider it like some kind of the density, and if you will provide like 2 directions in a space here and just multiply by the volume, you will obtain the mass and like the change in mass and multiplying with this change in volume. And basically he just uses the formula from the like Newtonian expectation here and substitutes the delta m using the formula at the top here, and here obtaining he is obtaining like the volume acceleration here due to the matter density, and he describes it like that. And from the other perspective, we have seen that the same quantity is described as using the Ricci tensor. So he kind of just equates those here, and because this applies to all observers through the same event, he says that it's true like for all TATB here, and therefore we arrive at like at the universal or like tensorial equation here, which says like that the Ricci tensor equals to minus 4 pi GTAB. And that was like the Einstein's initial proposal for the general theory of relativity. Yeah, but in this case we also have like a trouble with it, because the conservation equation leads to the corresponding equation with the Ricci curvature, which also in turn kind of leads to the trouble. And trouble with it is that if you will consider the Bianchi identity equation for the Riemannian curvature, we can contract it and like transform it to this form, which includes Ricci tensor and scalar curvature, and that scalar curvature defined by contracting the Ricci tensor here like that. So you basically use a metric tensor to move one index up and then contract it with itself. Yeah, so if you will transform it to that form, remember that's just like a Bianchi identity, then like we will have the trouble with the above proposed equation, because if we'll combine it with the contracted Bianchi identity, then it will lead us to the conclusion that the trace of the energy momentum tensor has to be constant through the space-time, so it should be like conserved. And this is really inconsistent with ordinary physics, probably because like we have different how how to say that, like different distributions, right, for the energy densities and pressures in the space. And in that case, we are kind of obtaining the flat picture in terms of the energy momentum distribution. Okay, so anyway, afterwards he just saying that like Einstein eventually concluded that for consistency, the two tensors satisfying the conservation equations should be equated, but like to within some constant factor, and he came up with what we know now as Einstein field equation. So basically he kind of considered like that one equation at the bottom here, and also this one, like his initial proposal. And you can see that this conserved quantity here kind of reminds this one here. And basically he kind of added here the scalar Ricci curvature here for the Ricci tensor. And as you can see, like that right part of the equation was kind of multiplied by 2 here. Probably because while contracting that one, we are obtaining 1 more minus 4 pi GTAB here. Yeah, and that's like the exercise here to prove, like to obtain that equation and explain why we have minus 8 here. Okay, one moment. Yeah, and at the end of that paragraph, he says, like, if you will consider having no mass, like when energy momentum tensor equals 0, this will be called like the vacuum Einstein's equation, and the vacuum equation becomes like this one, which could be written just as Ricci tensor equals to 0, and space with vanishing Ricci tensor is sometimes called Ricci flat. Yeah, so that's like the basic idea behind the Einstein's field equation. So basically what we see here is that curvature of the space-time will kind of impact the energy momentum tensor, and it's kind of the first part, like the curvature tells matter how to move, and this energy momentum tensor changes will change the curvature. So that's like the connection between the two. Okay, and any questions? Yeah, so just to summarize, basically you can see that like the whole idea is pretty simple, but to go through all of the calculation in details is pretty hard. Yeah, and anyway, you can trace everything here, like starting from chapter 17, from the like changes in volume of the two geodesics due to the like gravitational force in the Newtonian theory, and afterwards we can induce like Riemannian geometry and Riemann curvature, and after understanding what Ricci tensor is, we can kind of also prove something like that, like this acceleration of volume equation, and therefore just kind of deduce everything going on just to the like the final result we are obtaining at the end of the subchapter. Okay, so and in 19.7 the further issues with that is discussed, and first one is the cosmological constant. Sorry. And this is really like tiny constant, like which has really small magnitude here, like 10 to minus 55, and it has no direct observational relevance until cosmological scales are reached, and therefore it is called like that, like cosmological constant. And the quantity constructed from the Ricci tensor in the above expression is replaced with this one, like the lambda g here, and this will still like satisfy the conservation equation since the lambda is constant and the covariant derivative of the matrix equals to 0 here, and therefore we can include it and like the whole equation will still be true. Yeah, and Einstein originally introduced this extra term in order to have the possibility of static specially closed universe on the cosmological scale, but from Hubble's observations in 1929, we know that like the universe is expanding and therefore not static. And Einstein withdrew his support for the cosmological constant after Hubble's observations, and he been asserting that it had been his like greatest mistake, and perhaps he was saying that because otherwise he could have predicted the expansion of the universe, maybe. Yeah, nevertheless, that idea was reintroduced later. Yeah, and it was done like pretty recently, maybe like 20 or I don't remember, maybe 20 or maybe 25 years ago. So like the observation of the distant supernovas have led most theorists to reintroduce the cosmological constant or something similar to it, referred to as dark energy. And that was introduced as a way of making the observations consistent with other perceived requirements. And he says that, Penrose says that he will return to that issue in the later chapter 28 here. And he says that on his mind, like he thinks that he is rather reluctant to accept that nature would be likely to make use of that term. So basically Penrose doesn't believe in that cosmological constant, and he has some thoughts about probably how not to use that and explain the cosmological evidences somehow, like in the other way probably. Okay. Okay, so yeah, and yeah, and here he says that we can also include cosmological constant other way around here. So basically he kind of converts, like rewrites the Einstein equation using some kind of the dual form. I've seen that like somewhere, probably on the YouTube somewhere, that we can rewrite Einstein field equation using contraction of the energy momentum tensor. But anyway, he says, just states that we can do that, like we can write it like that in this form here. And here he discusses what is called like active gravitative mass. Yeah, and here he says like the active gravitational mass in Einstein's general relativity equals to the quantity rho plus P1, P2, P3, and that additional term with lambda divided by 4pg here. And he says that rather having the like that density equals to the probably like the pure energy density here, P1, P2, and P3 are the values of the pressure of the matter on three orthogonal special axes. Okay, so that's basically like discussing some kind of the like additional term to mass or energy from the like pressure terms and cosmological constant, and probably it will not impact anything like on a small scale, but he says here like for however the pressure contributions to active gravitational mass do play significant roles under certain extreme conditions, like when the pressure probably is really high, like a very massive star is getting close to a situation in which it is in danger of collapsing under its own inward gravitational pull, we find that an increased pressure in the star, which we might expect to help the star support it, actually increases the tendency to collapse because of extra gravitational mass that it produces. So basically he says that those pressure terms here, they kinda can induce something like a black star formation or something like that. Okay. Yeah, and here he just one more time tells us that TAB is something like a current. Okay, we have discussed that also. Yeah, and he asks here, like, we may ask what might be the appropriate analog of the Maxwell field tensor in the gravitational field case. And that's kind of pretty interesting question. And the answer is not the metric tensor, which is more analogous to the electromagnetic potential here. And some people might regard the full Riemannian curvature tensor as the analog to the Maxwell tensor. But actually, it's more appropriate to choose what is called the Weyl tensor or conformal tensor, CABCD here, which is like the full Riemann tensor but has the Ricci tensor part removed. And we have seen in the chapter 17 that we can have like two different effects on the geodesics. Like one is tidal forces and the other one is like volume changing part. And it's described like here. You can see like tidal forces is acting on that circle and kind of producing the ellipse at the result, and the other curvature effect is like volume changes. And we can call those like Weyl and Ricci curvatures here. And basically here the same thing is happening. So basically we are removing that volume changes part of the Riemannian curvature tensor, which is like Ricci tensor. And basically like to remove those, yeah, and he says here that the reason it's reasonable because Ricci tensor can be closely identified with the source TAB, so we need to remove these source degrees of freedom if we wish to identify those degrees of freedom that directly describe the gravitational field. Yeah, and therefore in free space where there is no matter, the Weyl tensor is equal to the Riemannian curvature tensor, but generally the Weyl tensor is defined by the somewhat complicated looking formula which removes Ricci tensor part from the full curvature. And he writes the formula down here for us. Yeah, and probably 1923 will be about what? Like show that all the traces of C vanish. Okay, that's not about the proof of that formula. Anyway, so the formula is given here in the explicit way, and basically we just need to understand the basic things that we kind of removing the Ricci parts from the Riemannian curvature tensor here to obtain the Weyl one. Okay, and at the end he says that we shall be seeing a key physical role for the Weyl tensor in the chapter 28, and the vanishing of this quantity is a condition for the conformal flatness of the spacetime. So basically I think that will play a role in like deducing the geometry of this spacetime or something like that. Okay, yeah, pretty hard subchapter, but like in basic terms, we just need to know that we have that cosmological constant for some reasons here, which are connected with the view on the universe as like static and specially closed. Yeah, and he hadn't said anything about dark energy here. I hope he will disclose more information later. I'm also not sure about that gravitational mass, but as far as I understood, it's just about like some kind of the processes in the stars and maybe like black holes formations. The most important part, and maybe the most understandable by me, is the end of that subchapter about the Weyl tensor. So basically, it's just the analog of the Maxwell tensor from the electromagnetic theory, and which is obtained like from like removing all parts of the Ricci tensor from the Riemannian curvature. So yeah.
So it seems like the difference between the Weyl and the Ricci tensors is kind of similar to how like Maxwell's equations are can be split up into the ones that include sources and then the ones that are homogeneous.
Yeah, it seems so. Yeah.
So is it that we can recover Maxwell's equations from these? Because I mean, these seem more just like purely geometric, just talking about curvature.
Do you mean that we can like somehow obtain the Maxwell equations from the like Einstein equation or what?
Yeah, that's my question.
That's an interesting question, but I don't know the answer actually. Like,
I mean, we talk about the energy and momentum densities of the electromagnetic field. So if you know the Einstein's equations about energy momentum densities, then perhaps we can recover the Maxwell equations. Or I'm also wondering if it's like just analogous.
I think you can, like the energy momentum tensor, there's a version of it where you can sort of plug in the Faraday or the electromagnetic tensor, and like you can get cases where electric and magnetic fields can curve space-time just the way that mass curves space-time. I've never heard of a situation where it acts as like a replacement for Maxwell's equations, though, where it like supersedes them. But I guess I'm not totally sure either.
Oh, I see. So like maybe perhaps a charged capacitor will bend space ever so slightly.
I think technically yes, but yeah, probably by like a super tiny amount.
Yeah, and maybe like the question you have asked is connected with this paragraph here about the theme called like space-time is just a background. And you can see here that like the space-time geometry serves merely as a background, so it is undisturbed by the fields within it. And moreover, the fields are unable to pick up the quantity in question from the background or lose it to background because of the symmetry. And like I'm not sure about the interaction. Like, do fields have a mass? Yeah, they should probably, right?
Well, I think that depends on the field.
But
like
they have energy. Like we can like calculate the energy in the electromagnetic field.
Oh, definitely. I mean, like if you integrate E squared, that's proportional to the energy density.
Mm-hmm. Yeah, and also, one moment, I will just bring another book. I just thought about the gravitation book and the equation I've seen there, where Maxwell equation used as the curvature. One moment. Just to compare, and probably like if you want to understand those things better, probably we need to read the gravitation book. So, oh, really big one. One moment. Like here you can see the same formula we have seen, or like really similar one we have seen for the acceleration of the volume change in the Penrose book. Like you have that d capital squared here, and change of the, that's probably like just a space-time vector, like acceleration here, and we have curvature and like some probably two more directions like to use here, and on the top you have a Lorentz curvature written in this similar fashion.
Oh, so maybe it's that all the stuff that we did with Maxwell's equations, that really only works with the Minkowski metric, but you have to use something else when it's not just the Minkowski metric.
Yeah, maybe that's it. Yeah, but yeah, it's pretty involved theme, and I think we need to read more of that to be able to answer those questions.
I dropped a couple links in the beta weekly meeting chat. They might be slightly interesting for further reading.
Thank you.
Oh, Mesocosmos asked a question.
Yeah.
He said,
what does it mean that Einstein didn't solve equations, but Schwarzschild found the exact solution? I'm not aware about the history actually, but probably Schwarzschild kind of solved those.
I think when you say you solved the Einstein field equations, it means you got the metric tensor G. So that's the thing you're trying to solve for. And I think Einstein did various things with the Einstein equations. Like I think he predicted Mercury's orbit be slightly different than what Newton predicted, which got him a lot of attention. But I don't think he solved for like the actual black hole, like the standard spherical mass solution himself. I think someone beat him to that. So someone got, I think they call it the Schwarzschild solution. It's like an expression for the metric G for like a spherical body, and Schwarzschild figured that out first.
Yeah, and actually at that, like at the 19.8 here, we will talk a little bit about the like confirmations of the general relativity and some historical aspects. So it contains some of the information about Mercury also. So I propose to finish with the last subchapter, and afterwards we will talk more just about everything, okay?
Sounds good.
Great, great. Let me recall a little bit. A moment. So in the first paragraph here, Penrose is talking about like the potential gravity field energy, and he kind of show us like two different systems with the same bodies, where we have like two bodies on different distances, and we know that if they're closer, then like the tension and the like potential gravitational energy is like probably bigger because of the closeness here, and he said that like the energy momentum tensor will be the same whether the two bodies are close together or far apart, and yet the total mass energy will differ in the two cases, and the difference would be attributed to the energy in the gravitational field itself. And in fact, it's a negative contribution that is more sizable when the bodies are close than they are far apart. Yeah, and under the picture here, he says that it is kind of non-local. Like imagine two planets, and if they are far apart, then the Newtonian negative potential energy contribution is not so great as when they are close together. And thus the total energy and hence the total mass of the whole system is larger in case A than in case B, despite the total integrated energy densities as measured by the energy momentum tensors being virtually the same in the two cases. Interesting. Like, do you understand why the total mass is larger in the case A? Because I'm not sure why.
Well, I mean, I think it's just saying because the potential energy is negative.
Yeah.
So if like the mass is given by the total energy, then the larger or like the more negative the potential energy is, then the less total energy there will be.
Yeah, so basically like the system in the picture A has more overall energy because of the potential energy being small.
Yeah, and it's just because it's 1 over r. So if you decrease r, then that subtraction of 1 over r in the total mass, it ends up a smaller value.
Yeah, and in the next paragraph, he is talking about like the bodies. If you put those bodies in a motion, like in a orbit around like about one another, and he says that it is a consequence of the Einstein's field equation that gravitational waves, ripples in the fabric of space-time, will emanate from the system and carry positive energy away from it. In normal circumstances, this energy loss will be very small. For example, in the Jupiter-Sun system, the rate of the energy loss by those gravitational ripples is only about that emitted by a 40-watt light bulb. But for massive and violent systems such as the final coalescence of two black holes that have been spiraling into each other, it's expected that the energy loss would be so large that detectors presently being constructed here on Earth might be able to register the presence of such gravitational waves at a distance of 15 megaparsecs which is equals like that quantity in meters. Yeah, so, and as far as we know, they already been detected, right, by the LIGO interferometer, right? Yeah, and we have like some videos in chapter 19 channel about those and the history of the detection, basically. Okay, and in the next paragraph, the double neutron star system is described. Okay, and here he talks about like neutron star, which is literally dense star, comparable with like which density is comparable to the atomic nucleus density. And he says like a tennis ball filled with such material would have a total mass comparable with that of the Mars moon Deimos. Yeah, and that system of the like double neutron star system was observed by the period of 25 years, and one of star is pulsar, which emits very precisely timed electromagnetic bleeps 17 times a second. And the timing of these signals is so precise and the system itself is so clean that comparison between observation and theoretical expectation provides a confirmation of Einstein's general relativity to about 1 part in 10 to power 14. Yeah, so it's pretty nice accuracy for like confirmation here. And this figure refers to the overall time and precision over a period of more than 20 years. Yeah, and he kind of starts with some history remarks. Here he tells us that there were only like 3 tests of the general relativity before 1969, and those 3 tests included like the perihelion advance of the planet Mercury. That was like one of the first one probably, and a second observational effect was the tiny bending of the distant starlight by the sun, and that's kind of one of the first examples given in the Gravitation book. And one more thing is slowing of clock rates in a gravitational potential predicted by Einstein's theory, and this was observed by Adams in 1925 for a white dwarf star known as the companion of Sirius. Okay, but a far more convincing confirmation was later obtained in 1960s. Yeah, and afterwards he talks about like one more experiment about some kind of the one more confirmation of the time delay, and he comes back to the theme of the observation of the gravitational waves here. So he talks about LIGO here, and he says that it is clear that Einstein's theory is now very well supported observationally, and the existence of gravitational waves seems to be clearly confirmed by the Hughes-Taylor observation, and Hughes-Taylor observations is that double neutron star system seen here, which you talked about. Okay. Yeah, and he's been saying here that observation was not a direct detection of such waves, and there are now several projects for the direct detection of gravitational waves, which constitute a worldwide concerted effort to use such waves to probe violent activity such as black hole collisions in distant parts of the universe. In effect, these combined projects will provide a gravitational wave telescope, so that Einstein's theory has the potential to give us yet another powerful way of exploring the distant universe. And that's actually what is basically is done by the LIGO experiment. and it was really done like a few years ago, probably. Okay, and at last here he goes back to the question about conservation of the energy and the question like what is gravitational energy. And he says here that despite some people's worries about energy conservation, general relativity has some very remarkable observational confirmations, and therefore we should return to the question of the gravitational energy. Okay, and he is talking here that like the gravitational waves indeed carry actual energy away from the system, and the energy momentum tensor in empty space is zero, so the gravitational wave energy has to be measured in some other way that is not locally attributable to an energy density. So basically he kind of saying that we cannot measure gravitational waves using the same tool we've been using for the general theory of relativity, like the energy momentum tensor. And gravitational energy is a genuinely non-local quantity, and it sounds bad because like in physical theories we have like principle of locality, so probably he will need to fix that later. Okay, so yeah, he says here that it doesn't imply that there is no mathematical description of gravitational energy, and that he believes that it is fair to say that we don't yet have a complete understanding of gravitational mass energy. There is an important class of situations in which a very complete answer can be given, and these situations are those referred to as asymptotically flat, as they refer to gravitating systems that may be regarded as being isolated from the rest of the universe, and essentially because of their very large distance from everything else. Okay, and he says here that like double star system like Hulse-Taylor binary pulsar, in which one is conserved with the energy that is lost through gravitational radiation. Like in that case we can kind of provide some mathematical framework for those. And the work of de Bondi and his collaborators, as generalized by Sachs here, probably he provides some answers for those, like there is some mathematical theory to describe those gravitational waves for those systems. Yeah, and basically that's what he's saying here, that there is a clear-cut mathematical accounting of the mass energy carried away from such system in the form of gravitational waves, and a conservation law for energy momentum was accordingly achieved in that case. And here we have some picture here, and basically, as far as I understand, we have orbiting bodies here moving in the space-time. So basically we have those like helicoid trajectories here over time, and time goes up here, and he shows like dissipating gravitational waves here, like removing some energy from the system, which goes to something which is called null infinity. And he said that we will talk about the null infinity later, and a geometrical notion of that will be discussed in chapter 27. Yeah. Okay, and here he also talks about that. He also says about something about the non-local character of that law. Yeah, and about special isolation of the system from everything else. So it's basically like some kind of the idealized example which kind of works on the big scales probably here. And there is something little miraculous about how things all fit together, including certain positivity theorems that were later proved, which tell us that the total mass of a system, including the negative gravitational potential energy contributions, discussed about cannot be negative. So I've heard that probably Xintan Yao was working on something like that about theorems of the mass positivity. So basically it is probably like a theorem that gravitational potential energy should be positive. I mean, like the total contribution to the system cannot be negative. So we cannot obtain like the negative mass in the system. But that seems like some kind of the expert topic for me. Okay, and yeah, at the end here, he just says that there are general prescriptions for obtaining conservation laws for systems of interacting fields. And these come from the Lagrangian approach, which will be introduced in the next chapter. And the Lagrangian approach is very powerful, general, and beautiful. Yeah. So basically, he kind of just invites us to the next theme and talk about Hamiltonians, Lagrangians, which is the theme for the next chapter, actually. Yeah. And basically, just to summarize that subchapter 19.8, so basically he just talks about gravitational waves here, gives us some information about negative potential contribution of the gravitational energy in like the system of two planets on the figure 8 here, and also talks about some observational confirmations, history of the general relativity, and just kind of scratch the surface of how we can understand the gravitational energy, how we can describe it. But in that case, he just given some notes, so no mathematical formulas even for those here. And basically, I think that to understand those better, we will need to use Lagrangians, Hamiltonians, and probably we should know also quantum theory. And that's probably the reason why the discussion of those like more deep questions will happen in the later chapters, like 27 or 28. Yeah, so basically that's it. Now let's discuss. Any questions? Let's talk.
Wonder about this, the dissipation of gravitational waves. So I wonder if there's a redshift, like, the same way how like distant stars have a redshift. I wonder if there would be a similar effect with gravitational waves.
Yeah, I feel like I need to Google for it. Maybe anyone heard about redshift for gravitational waves?
I would think yes, but it just seems kind of like a bit off the intuition of, well, it's due to the acceleration of the size of volumes in space. I would think that because of the expansion of space-time, photons got redshifted, and since I don't know, this is not the right assumption. I'm kind of assuming that the medium for photons would be the same as the medium for gravitational waves, and I think that would be a reasonable assumption, but maybe it's not. Because if they do share the same medium, then as that medium expands, then the relative proportion of the wavelengths should increase as well. So that will give you a redshift.
Yeah, and actually I have found on the Wikipedia that there is a gravitational redshift.
No, but this is just photons. I see it here. This is still photons. I don't think this is gravitational waves.
Yeah.
Does it see in that figure there, redshift of the light?
So it's not about the gravitational waves. Okay. Okay. Then there is the answer on the physics stack exchange. I will share it in the... Oh, I think you can see it on my screen, right?
Yeah, I can, and I think it is okay. So it's talking about since it propagates at c, and so I think that my assumption is right, that since the medium is the same, that they'll be redshifted similarly. Because like both photons and gravitational waves are waves in space-time, and so if the photon can experience a redshift, then so could the gravitational wave.
What, like, if we are thinking about the medium here, then the medium is vacuum or something like that, right?
Well, it's space-time.
I mean, I haven't studied gravitational waves very much, but like I would have said, the way I would have phrased it is that photons are like a disturbance in the electromagnetic field, whereas gravitational waves are a disturbance in the curvature of space-time. So I don't know if they would sort of belong in the same category or not, but I'm kind of talking without much experience here.
I see. So you're saying, like, because we can represent like the photon field, that makes it distinct from how gravity waves are just in space-time and not like in a gravity field of its own.
Like the one thing I do know, I guess that's sort of what I'm saying. The one thing I do know about gravitational waves is that it's basically the metric is the thing that's sort of vibrating, I guess. And I've seen when you first talk about gravitational waves, they sort of take the metric G and then they'll add a small disturbance H to it. I think it's sort of like a perturbation, like you might have seen in perturbation theory and quantum. So I think it's like it's the metric, which I guess also ends up being the space-time curvature itself, that's sort of vibrating, and that's what the wave is. I think that's what it is.
Yeah, perhaps perhaps they'll dive into it in the subsequent chapters.
Yeah.
Although I think this book was written before there was much experimental confirmation.
I think like that to talk about photons, we also need like quantum theory, and basically I think that's the plan which like Penrose is preparing for us. Like he just want to talk about Lagrangians afterwards and jump up into the quantum mechanics, and only after like knowing something about quantum mechanics we will kind of try to merge the approaches, and then talk from the like general perspective.
That's interesting. I'll keep my eye out, because I wonder if there's any quantum field theory predictions for redshift at large distances, because I think QFT is all for like short distance stuff. It's supposed to be super general, but I wonder if there's any gravitational redshift in QFT. I would think that's excluded.
Yeah, like the problem here is that we don't have any like alternative tracks of going through the Road to Reality book currently. So I'm kind of assuming that the natural chapter order is the way to go.
Yeah, I agree. And with all the references that he's got in each chapter, it's quite nice.
Mesocosmos sent something about M87, and it's some kind of the galaxy or black hole. What is that? Do you know?
I think M87.
What?
I think M87 is a black hole.
Yeah, and actually on the Scienceclic here at the last video. Oh, well, I have some probably grammarly at here. Okay. At the last video here, you can see like the basic approach to solving the problems in general relativity, and here he has a scheme. Probably one moment. Yeah, somewhere here. Yeah, so, and basic scheme is like that. So that's like different approaches to solving problems in general relativity here. So basically, like, we need to start from metric, and we kind of, for different tasks, we can choose different metrics, and for different metrics, we can choose different coordinates. Like Minkowski metric provides us with Cartesian coordinates usually, and we have Schwarzschild metric with Schwarzschild coordinates, and the kind of spherical ones. Yeah, and there could be a case when we don't have a metric pre-calculated for the current situation. And here we can see that, like, from the coordinates and like from the description of the system, and by using Einstein equation and solving it, we can kind of derive the metric. And that's like that back loop going on here on the screen from coordinates to metric. And like after obtaining our metric here and like simplifying all overall solution due to the symmetries, we can have like two basic cases here where we are concerned with velocity or acceleration of the object in the system. And this kind of also includes a few examples of those situations. So yeah, I don't remember those, but anyway, I think that this video will be really good addition to the chapter 19. I'm seeing that Chris sent us some information about Newton-Cartan theory. And that's exactly the theory Penrose was talking about, Chris, in the chapter 17. We've been discussing that. Probably it's like 17.5 or so. We've discussed that theory a little bit, probably 2 months ago or so. And Penrose, there, he said that he will use it later. And basically that's the scene he was using here to deduce the Einstein equation in chapter 19. And he will talk more about that in chapter 30, actually. So I think we will hear about Newton-Cartan theory later also. Yeah. Probably you missed that call, but this call is also recorded, and you can kind of consult the video on the YouTube, or you can just read a little bit more in this chapter 17.